Alright guys, so where we got to last time is we wanted to try to get the added unknown table amounts. The one addition is pretty simple. We kind of have it already set right here, but the problem that we're going to face is in this one right here, the flop. And the flop is probably one of the biggest points that we need to consider in poker, because in the hand pre-flop, that's basically a very difficult and very narrow possibility of what to do. Basically, you either know what to do or you don't. Some people do it on luck. Some people pretty much just bet anything in order to see the flop. Once you see the flop, you must be able to make some kind of educated guess. Now, the problem is there's about 2 million possibilities when the flop comes up for the other players. It's very important here to realize that I just said the other players, because in the case of the player himself, we already know 5 cards, we're only missing 2 cards. 2 cards is pretty much about 1,000 combinations only, as we have seen in the previous episode. So what we need to do at this point is to figure out a way to get these 2 million possibilities done easily and quickly so that the computer does not take a long time to process. The best that I could come up with is to eliminate, or to try to re-eliminate, the cards that are known in the 2-card combo deck that we just added. So here we have a hand plus table, right? This hand plus table, let's do the following. Let's get an array size. So the array size, do we need it here? No, I think we need the array size right here. And let's create an indicator. So the array size at this point is 1,000. There are 1,000 numbers. Each one of these 1,000 will need to, basically, if we're going to add another 2 cards, right? So 2 cards is another 1,000. We have about 1 million. Mathematically, it says we have about 2 million combinations. Hopefully, we can do it with 1. So what do we do? What we do is the following. We are going to take all possible hand combos that we have earlier, right? If you guys remember, in this one, I'm going to go ahead and show it right here, and I'm going to keep it just briefly sitting on the side for now. These are the combinations. We'll deal with these. Oh, nope, not bad. We'll deal with these later. And let me run this again just to have some numbers into this array. The first one is us. These are the other players. Each one of these needs to have another 2 numbers associated with it. Now, thankfully, we already have a table like this ready and waiting for this system. What we could do, we could do many things here. One thing we could do is to take this array and basically redo this to it. Now, knowing only 2 numbers, the fraction, the percent of the knowns that we are going to be altering is tiny. So we know 3 cards on the table, plus 2 cards in your hand. We know 5 cards. But the truth is, we also know 2 unknown cards. So we actually know up to 7 cards. These unknown cards are these cards right here. 414, 413, these are all considered unknown. And this would eliminate another 2 options of each mathematical inquiry. So now we have 52 minus 7. We literally have 45 possibilities per one that we need to consider. So 45 times 44 divided by 2 for the factorial is 990. 990 times 1000 was 1036. we are a little less than 1,000,000 combinations for everything. 1,000,000 combination is still a lot. Now, a single interesting kind of beautiful aspect of this is that some of these possibilities will be manifested again in the first 1,000, right? So what I mean by this is that if we actually go back here and look at this table, so first one, let's go ahead and solve this for the first and second, so you guys will understand what I'm saying. What we need to do is take our full set right here, array 4, and we're going to have to index it, obviously, for every single number. I'm going to keep this big for now until we figure out exactly what we're going to do, and I'm going to run it only once so that we only process the the player's cards. So the player's cards, these are all possible combinations. These here have eliminated our known cards from deck. So this number here should not include anything that we know. Let me see. I'm not really sure where I'm going with this, guys. I'm sorry. So we insert this and disable the indexing. Now what we need to do is we need to add a 2-card combo. So this will actually not work here. What we need to get is our 2-card combo deck right here, and we will need to take each one of these. So another for loop in the first for loop, where we are taking no, each one of these only has 2 numbers. We already know that. So what we do is we take the 1,000 something numbers. There's 1,000 different combinations in here. We can actually go ahead and check this if we would like to. Oh, let's bring this back. I always do the same mistake. Okay, let's bring this back here and see what we have and run it. 1,035 different combination. This is 1,036 because we added just the player to it. So we have 1,035 combinations. So this will run 1,035 times for every single one of these. So it's going to run 1,035 times 1,035. It is an insane amount of processing time. Literally. 1,035 times 1,036 to be exact. Okay, so what's going on here? Here, what we have is the 2-number combo right here. So what we have in here is an array of hopefully just 2 numbers, and those are the 2-number combinations that come out of here. Those are this array basically. So what we're getting now is 414, 413, 414, 412, 414, 411, and so on and so forth. Now what we need to look at is the equality between all those. So there's going to be 2 of them in here, and there's going to be 2 of them in here. Let's disable this indexing, and if we put another for loop, I know this is a crazy amount of for loops. It's crazy how many for loops are coming in here. But there we go. Now all we need to do is test whether those 2 are equal to each other or not. Out it from here, out it from here. Now I'm going to run this only once, not 1,035 times, so you guys will see that here I should get a 2 by 2. In theory, I should get a 2 by 2 array that represents what's going on. And there it is. Everything is false, so we're fine. If I run this twice, and the reason I run that twice is because when I run it twice, we're going to get this number, and then the other one runs once, which gets this number as well. In theory, we should get 2 of these lights to light up. There they are. If we go ahead and try this for the third one, we should get 1 light to light up. If you understand how I know which lights are going to light up, then you have a very good grasp of what's going on here. Yeah, so there we go. So now all we need to do is basically create an AND system, and I believe you do that in the Boolean AND array element. Is it AND or is it OR? I'm not sure. I think I'm gonna go with OR. Let's OR all these elements, because basically if any one of these is on, that means that, okay, so what's going on is we're getting this combo and we're putting it right next to this combo. I'm gonna create a temporary indicator here so you guys will see what I mean. And there we go. So let's run this. Perfect. So now what we're doing is, when we run this 3 times on that and 1 time on this, that means we're checking the third number here, 414, 412, with this number here, which is 414, 413. And as you can see, 414 equals 414, yes. 414 equals 413, no. 412 equals 414, no. 412 equals 413, no. When I do this with 2, this one, you're going to get 2 matches, 414 equal 414 and 413 equal 413. So that's what happens when I did this 2. That's what happened. So 414 is equal to 414. 414 is not equal to 413. And then it does it again. In essence, only these 2 numbers will light up. The only time these may or may not light up is when we are dealing with the player right here. So I'm going to consider it just for the player. This actually would create probably a huge amount of overlap, because if I were not to include the player, if I were to do that as a separate step, actually, we might be able to save on all these systems over here. And the reason that is, this is making me think we probably should consider that, exactly what I just said. Because by looking at this, what's going on here is that we are doing an intense check on what's going on. As you remember here, it always makes sure that the first number is bigger than the second number. Therefore, as I said, we can only do check on the first equal the first or not, and the second equal second or not. We do not need to check if the first is equal to the third, because 414, actually, interesting, guys. Let us go down the list till we get another one. Let's pass the 414s and get to the 413s and see what happens. 413, this is definitely smaller than it, but there is a 412 here. So this one, let's see which ID number is it. This is ID 46. Let's do number 46 just to see what we're gonna get, because the top one has 414, 412, so we only got this one. Just to make sure, 414, 412, oh, this might be, let's try 47. Aha! So 47 created this green, which means what I was saying is actually invalid. We do need this system. This array will give us an AND OR, create an indicator. So if anything, if any one of these 4 is green, this is green. And we're going to have to keep that this way. This is going to be the true or false that will determine this. Let me go ahead and condense this little part and get back to you guys. Alright guys, here we are. So now what this true or false is telling us is whether or not the two number combo that is being developed here works or not with the previous 2-card combo. Now this new 2-card combo is going to come in a ton of varieties. And what I would like to do is be able to take all that and add it to create a new, even bigger, more complex array to test. How do we do that? And for some of you, what does what I just said mean? Well, what this means is that what we have here, not here, here, right here, is this possibility matrix. Now we're going to have to take this matrix and add to it all the new possibilities that we have for every single point that we have. Now this here size is 1036, this here size is 1036, that's the one that we are inputting. So we can actually input this array seamlessly into the system, and this point all the way into here, disable indexing at this point right here is now similar to this point right here. Basically all we need to do is redo this step right here as many times as necessary. Sounds pretty simple, doesn't it? The premise of what's going on here is that this array is breaking apart in here, basically giving us the option of every single one of those. Now every single time one of those is created in this loop, I would like it to keep adding to itself, basically just like this does, and come out as a tunnel and then come out as another tunnel. If we double tunnel this, the array will not work, so that will not work. I'm trying to figure out here how this would be done in a safe way. So we're taking each one of these at the specific point. So for the 0th one, it would be this would be the 0th array, for example. So we take this and we're gonna add to it every single one of these if this is false, right? If false. So if false. If true, we don't do anything. If false, we do that. This system is very similar to things that we have done way back here, I believe. No? Where did we do the true or false, guys? Do you guys remember that? Did we do that up here? Huh. Cannot seem to find it. Irrelevant. So, we come in here, and if false, we need to add those two into the system that we have. So what we do is, first I'm going to lower this because I'm sure we're not going to need any higher space. What we're going to do is we're going to have to take the new two numbers right here that do not match, that do not interfere with the old two numbers right here. And what we're going to do is we're going to take this system and we're going to apply to it. We're going to take this right here, which will take an input from that, whichever level point this is at, and we're going to add to it this array. So now this array is added to this point, and at this instance where all this has occurred, if, basically if and only if, I love saying that, if and only if, this one allows it. So this should be false for this to occur. What ends up happening if this is false? So we're going to put this in a case structure. If this is, make this case false. And I'm going to lift this up here just to have it. So in the false, if this is true, nothing happens. If this is false, something happens. Now, in the false case, we're going to take in whatever this was, we're going to adjust it to our own needs, and above that, we are going to have to insert it into, we would have to insert it into our new system. So if this is okay, we would need to insert it into a new system that we have. So let's add that in here. So we take this and we array, insert into array this new element into this array, shift register all the way through, come back out through the shift register, all the way back out, and show me what you are. So why is this not working? This should not have any issue with what we are doing. Let us do a build array system maybe. There we go. And let's create an external constant and create an indicator to diagnose what I just did. 1. Let's do this once and this once and see the difference between those two. I'm actually not sure what we just did, but it should be comparable to array number 7. So let us see how comparable is array number 9 to array number 7. Okay, so 0th case gives us the wrong answer, I believe. Or is that the right answer? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. How come we have 8 numbers here? How can we possibly have 8 numbers? Okay, so we are doing this once. We are doing this once. Therefore, we shall end up with only one answer. Okay, let's go ahead and do this 10 times. Just to see what's going to happen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. Okay, let's go back to 0. What just happened here and why? This 1, 2, 3, 4, 5, 6 cards. Let's see what state are we in. What state are we in? We are in state turn. And on the turn, if we come here, on the turn we have 4 cards plus 2 in our hands. We have 6 cards. We should not be in the turn. We should be in the flop for proper testing of this. Let's run this again. There we go. 1, 2, 3, 4, 5. These are the 5 cards that we have here, plus those 2. This will run for every single possible combination that there is. I would like to make the index bigger, come here, and I'd like to let this run wild. 1,000 combinations. Let me see how long this will take to process. Oh, that was fast. So now we have all 1,000 different combinations that are possible with 3, 4, 5 cards and this one. Now the beauty does not begin until we pass our first 1035 combinations and go into our second 1035, and we're still not done. That's interesting. There's more than 1035 combinations here. Oh, there's 1080 combinations. Let's run this twice. So that's going to run 2000 almost combination. And now when we go 1081, we should jump from the known to table 1, where we have 1, 1, 1, and 1, 1, and 1, 1 right there. And those will be there. Now, I'm scared to do this, but this needs to be done, I would assume. We need to evaluate how long do you think it will take to process the infinite number of things right here. So I'm going to create an indicator right here and an indicator right there. So numeric and numeric 2. And now each one of these is going to keep cycling up to 1035. And I would like to see at the end of this what my array size is for this system. Oh, too far. There it is. This will probably consume the maximum amount of my CPU. So I'm going to save. And I hope this works. Let us do 2 million combinations. Go! Okay, so by looking at this, you can clearly see this will take an unbelievable amount of time. We're only on number 7. 8. There's 1,000 of those that need to be processed. I'm going to attempt to stop recording and run this again to see if there's any improved performance, because right now my CPUs are running at about 75–80%, so my laptop's at its max. I'll be back. So what I have noticed is that is unbelievably slow. We're still at 18. This is going to need some Google servers to process. So this entire episode we tried to get this to work, and it seems that even though it does work, as we can see from our array 9, this does work. This will produce these 4 here. The 2 million combinations can be produced, but it will take an incredible amount of time to do that, and we obviously do not have that luxury. So until we have better, faster, unbelievably faster processors at our disposal, we should not have to do this. That is pretty sad. I'm trying to think if there's any way that we can make this run faster, but we're dealing with already 1,000 unknowns, and we're adding to that another 1,000 unknowns. That is way too much. So what can we do? I'm gonna actually pause for a second and figure out what I could do or cannot do and get back to you guys. Alright guys, so after thinking about this, I would say that having the 2 million combinations, trying to figure out the 2 million combinations, is not worth it. So I'm going to get rid of that entire thing. What I did notice or think about is that the combo that we have will come in here and affect our array 8 and the flush that we would possibly have. Now what I was thinking of is that every single one of these are going to be creating an array possibility based on 5 numbers in this case. So 3, 4, 5, not 7. So these last 2 could be added artificially into this system. So by artificially adding it, basically means that, okay, so we have the array that tells us, we already have this array here that tells us basically how many there are, right? And I'm gonna just re-get that array right here, and there it is, and run the system just really quickly. There we go, we have 2, 2, 1, 0. Now possibility of adding 2 extra numbers means that the probability of getting a flush is going to be the added effect from these numbers plus 2. So it could either be 1, let's see, 1, 1, 0, 0, or it could be, and so on and so forth. So it could be 1, 0, 1, 0, and it could be 1, 0, 0, 1, and then it could be 0, 1, 1, 0, 0, 0, I'm sorry, 0, 1, 0, 1, or it could be 0, 0, 1, 1. Those are all the possibilities of 1s, and then it could be 2s, so it could be 2, 0, 0, 0, it could be 0, 2, 0, 0, 0, 0, 2, 0, and 0, 0, 0, 2. So here are, I believe, all the possibilities of putting 2 extra numbers into a flush. Now, by doing it this way, we actually eliminate something we eliminate the possibility of knowing what the highest card in the hand is. I could tell you if you get a flush or not, but I cannot tell you which flush you get. Obviously, when you take this and apply it to this, we're going to have to this side, we're going to have a lot more possibilities. But you can easily see that in this scenario, for example, the possibility 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only 10 combinations. The possibility to get a flush is 0. Now let's assume this was a 3, then the possibility is 1 out of 10. If this was a 4, then the possibility becomes 3, 4. 4 out of 10. Possibility is 4 out of 10 of whatever the flush is, times all the others, because we have 1,000 of them. So that is going to be a big number, but this is how we can do it later on. I'm going to leave this here for now. So this was a failed episode. These 2 million is just way too much. So this is going to be no way. This is going to be artificial later. This one should be easy, so we'll try to just go ahead and add this. But if we're doing the first one artificial, why not do this artificial too? It's an option, right? And then nothing's done here. So why not just do them all artificially without adding anything? So if we add to the turn, we get more accurate data. The turn will tell us exactly what to expect later on. Alright, so let me get rid of this, and what I will do is I will see you guys next time. Bye.